Now we're going to go over, I guess you could call application problems. I don't know if you'd call number 5 an application problem, but number 6 definitely is. But this one's kind of working our graphs backwards. So in the last video, we graphed a rational function from scratch, finding all kinds of information, our asymptotes, our intercepts, and any holes that we had. Now I want to see if I can kind of work backwards. Once you are given your graph of your rational function, can you answer the questions from it? So let's just kind of talk about this graph for a second. The blue lines here are my actual rational function. And I did this in Desmos, and Desmos doesn't do arrows, but we do have arrows on the ends of all of these. And then I have 2 different asymptotes here. So the first thing I want to know is my domain. Well, if I go back to my last example of graphing, I am told that the domain here couldn't equal plus or minus 5 because why? Because of a hole and a vertical asymptote. So that's what I need to look for when I'm looking for that domain. Do I have any holes in my graph, and do I have any vertical asymptotes in that graph? So here, when I look at my rational function here, I don't see any holes, but I do have a vertical asymptote. We have a vertical asymptote right here at x equals 0. Let me put VA. Vertical asymptote right there at x equals 0. So therefore, my domain is the set of all x such that x cannot equal 0. Now, we haven't really been dealing with range very often, but range only occurs if we, again, look at this graph. The only places that my range would not exist is if I had a horizontal asymptote. Here, however, I don't have a horizontal asymptote. I have an oblique asymptote. So if I don't have any horizontal asymptotes, I'm just going to cross that out right there. My range is all real numbers. Okay, x-intercepts, where is this crossing? The x-axis, and it is crossing right here at -2, 0, and 2, 0. Any y-intercepts, we always have a y-intercept with the exception of a vertical asymptote at x equals 0. So because my y-axis is an asymptote, that means I don't have any here. Vertical asymptote, we talked about this several times. It is at x equals 0. Horizontal, we talked about with a range. I don't have any. And then my oblique asymptote. My oblique asymptote is in the form of y equals mx plus b. So I need my slope and I need my y-intercept. Well, here's my oblique asymptote. It's crossing right here at 0, 0. So my y-intercept is at 0. And then my slope from this point to this point here, that's why they gave me this point. And notice it is hollow, it's on that asymptote, so it doesn't exist. They're just kind of helping guide right here. Rise over run gives me my slope. So from 0 to 6, we are rising 6. And then how much are we running to this point that they give me? We are going -2, since we're going to the left towards these negative numbers. So my oblique asymptote is at y equals 6 over 2 reduces to -3, -3x, and you can put plus 0 if you want, but it's not necessary. So my oblique asymptote is at y equals -3x. Okay, and then our last example, we're gonna do this all together here. I got this from my math lab, so this is more of a setup, but it says a steel drum in the shape of a right cylinder is required to have a volume of 700 cubic feet. So the volume of a cylinder is V equals pi r squared h. We need to write the height as a function of radius r. Is this a rational function? So I'm going to take my function here. I know I have a volume of 700. And now I need to write the height as a function of r. So we need to solve this for h, right? The height h as a function of r. So what's going on between pi, r squared, and h? Those are all being multiplied. That is pi times r squared times h. So the opposite of multiplication is division. So I'm just going to divide all of that over. So those cancel, and so I'm just left with h. Now I'm going to rewrite the order, and we're going to do h equals 700 divided by pi r squared. So there is my height written as a function of r, since r is the only variable in there. And then it wants to know, is this a rational function? Well, because I have a variable in that denominator, yes, it's a rational function. So that's why it's an application problem in this unit or in this lesson. Part B goes on to say that the surface area of a cylinder is S equals pi r squared plus 2 pi r h. We need to write the surface S as a function of r. Right now, this is, I guess, kind of a function of r and h. So I need it only in terms of r. Well, luckily, I know what h equals. H equals 700 over pi r squared. So we're going to substitute that in here. So I have S equals 2 pi r squared plus 2 pi r, and then my h is 700 over pi r squared. So if we simplify, we get 2 pi r squared plus 2 times 700 is 1400. And then here, my pi's will cancel. And then I have 1r and then an r squared. So 1r will cancel. And so this will be all divided by, or not all divided by, but 14 divided by just the r. So again, is this a rational function? Yes, because we're dividing by a variable here. Okay, and then lastly, graph the surface area equation on the window and then find the minimum. So this right here tells me my x's. You can see my x min is 0, x max is 10, and the scale is all going by 1. This is my y information. My y min is 0 to a y max of 1,000, and the scale is going up by hundreds. So let's graph this real quick and see if we can match this graph, and then we're going to find the minimum. So I am typing in this right here. It says graph the surface area equation. Here's my surface area. So we have 2 pi, which is second caret key. And then instead of r squared, we're just doing x squared. Plus 1400 divided by x. Now, if I hit graph and I don't change anything, I'm not going to get a lot of information, because if I'm in the scope of this graph right here, I am right in this like little section here. I am way too zoomed in. So we've got to change that window. We're going 0 to 10 and a scale of 1, from 0 to 1,000 with a scale of 100. So match this information right here. And now I'll hit graph. And now we have that shape. Okay, it looks a little different since this is more square or even more rectangular up. Ours is rectangular, kind of going side to side, but same thing. So then to find the min, we need to go to calc. So second trace, and I want to find the min, number 3. So my min is somewhere down in here. So I'm going to go to the left of it, and I can see here I'm starting to like slope up. I'm going to hit enter. Then I'm going to go over to the right side of that min. You can see right here I'm starting to again slope up. So my min is somewhere in between these. Hit enter. And we get what I have on this page right here. 4.812 and 436.429. Okay, so that is the min. So what we have found is if I have a radius of about 4.82, I'm going to get a surface area that is the smallest amount with a volume that still meets that criteria of 700. So why is that helpful? If I'm the one building these steel drums, I want that surface area to be the smallest amount. That way I don't have to use as much material to build this. All of these here have a volume of 700, but as it keeps going up, now my steel is going to be more and more, meaning I'm having to spend more money to get the same result here. And so this gives me my radius of my smallest surface area. And then I think it goes on to say in your homework something about like, if steel costs $20 per foot, how much would it cost to construct this? So you'll need to multiply the amount of material we need, that surface area, times however much the steel is costing for that particular problem.